is equal to, just add all of those numbers up. And get 0.2004. So sigma squared is the variance, and sigma is the standard deviation. So if I take the square root of that, sigma would be square root of 0.2004. Now we get 0.4477. So again, I know we're still in the land of theory, and it feels awkward. But again, the idea is, if I were to ask thousands and thousands or millions of people, how many days did you work last weekend? And we gathered all of those answers, and then I took the standard deviation of all of those answers, I should get something very close to that, like 4477. This is a random variable. Is that okay? How are we feeling so far? Yes?
I know it sounds silly, but like if you had 0.14 days as the average, could
Yes.
you add 0.4477 in either direction to get like the highs and lows, or does that not make sense?
Okay, sorry, when you say highs and lows of
Like if they could fall into like a box plot, how we did with the other standard deviations.
okay. So what you did with the other standard deviations, I think, was the empirical rule, which applied only to unimodal and symmetric distributions, where it had like plus or minus 1 standard deviation, plus or minus 2 standard deviations, and things like that. That applies only to unimodal and symmetric distributions, and this is not unimodal. I mean, it is unimodal, but it's not symmetric. Okay, and so you could do that, but the result you would get would be essentially meaningless, okay, or not very useful. But yes, you can use the standard deviation of this thing in the same way you would use standard deviations of many other things. But in our particular case, because it's very skewed, it would not be as useful. Yes?
I'm trying to understand what you just said. In chapter 1 and 2, didn't we learn that, like you just said, we don't use standard deviation and the mean when we're talking about something that isn't normal. We use median and IQR.
Yeah, if it's skewed, we generally use, we would prefer the median and IQR.
Is there an equivalent when we're talking about random variables?
Yeah, with random variables, we don't have a median and IQR equivalent, no. We're going to still be dealing with the mean and standard deviation for random variables. And that's okay, all right? This will all come into play. But I just have to kind of present this kind of theoretical stuff that, yeah.
So we still use means and
Yeah,
deviation,
so
it's not.
I might present a discrete random variable very similar to this on a quiz, and I might ask you to find the mean and the standard deviation of a random variable. Okay. And again, this does not represent data, okay? But the concept of the mean of a random variable is as if you were to go out and gather data. What would the mean of a very large data set be? That would be very close to the mean of your random variable. Okay. perhaps, okay, and we're not going to go through with this example. So I feel like maybe the example I used, it is an example of a random variable. If we pick a person at random and ask how many days of the week did you work, but maybe here's another example that might be easier to understand. Let's say in Las Vegas, you go to Las Vegas, you go to gamble, and let's say they have this big wheel, okay? And they have these games, right? And you spin the game and you just put a bet on what number you think it's going to land on. And if you get it right, you get money and stuff like that, okay? And they're all very different, but let's say in this one, the game looks like this, okay? And so this says so this you win 0, or I would just maybe not lose, but you win 0. And over here, you win $1. $1. Here you win $5. Okay. So in this case, what is the mean? I guess we're going through with it. The mean that you would win. Okay. So we don't, assuming it's fair, okay, and in Las Vegas the gaming commission makes sure that all the games run fair. Okay, they'd get in big trouble if it didn't. And let's say my picture was good. Okay, what are the outcomes that we would get? 0, 1, or 5, right? Okay, well, what's the probability of getting 0? I'm sorry, probability, yeah. What's the probability of getting 0? 75%. And what's the probability of getting 1? 1/6, 2 out of 12. So 1/6, or 0.1667. And then over here, getting 5 would be 1 out of 12. 0.0833. Is that okay? And so the mean you would win would be 0 times 0.75 plus 1 times 0.1667 plus 5 times 0.0833. Okay. And so so the average amount you would win if you played this many, many, many times would be 58.3 cents per game. Okay, that would be the average amount you win. So if they charge you $1 to play, this is a terrible game to play. Okay, but if they charge you 60 cents per spin of the wheel, you would not lose your money very, very quickly. Okay, you would lose money, but it would be a slow loss. Okay, and if they charged only 50 cents to play, you should play this all day. Okay, because even though you're going to lose or win $0 75% of the time, the 1 and the 5 outweigh it, and you'd be making 8 cents per spin. Okay. Is that good? Okay. So that's how a random variable works. Okay. We're only covering the discrete case in this class. The continuous case requires calculus, which is not a prereq. But basically, you're just going to turn the sum into an integral, and it works out. Okay, so we have a random variable. I want you guys to be able to find the mean and standard deviation of a random variable. And then we have, I guess, a special case or a certain type of random variable, which we call a binomial random variable. Got just enough time. Okay. So binomial random variable. This is a special kind of random variable. Okay? And again, a random variable is the outcome to a random event where the outcome is a number. Okay? In a binomial random variable, what we're essentially doing is we're repeating essentially a coin flip, but not necessarily a coin flip. We're repeating a random trial a certain number of times. We say that n times. So we repeat a random trial n times. So maybe I choose to flip the coin 6 times. Or I choose to do something n number of times, okay? Each trial has only 2 outcomes. Okay? And we label these, there's an arbitrary label of success and failure, okay? But these are just arbitrary labels. So a coin flip, either the coin lands heads or it doesn't, okay? And if we label heads as a success, then every time it lands heads, we would say success, and if it doesn't land heads, it's not a success. It's a failure, okay? But it could be anything, and so we just arbitrarily label things success and failure, okay? So it could be a family or a couple decides to have 4 children, and the child is either going to be a boy or not a boy, or girl or not a girl, depending on how you're labeling these things. Okay? And you have to just label one of these things success and the other thing failure, okay? But these are, again, these are just arbitrary labels, and so it's not so much that success is something we celebrate and failure is something that is disappointing. It's just it either happened or it didn't happen. That's probably an easier way to think of it, but the literature calls it success and failure, okay? And every trial has the same probability of success. Okay. And each trial is independent of the other. Okay. So these are the conditions that must be true for binomial random variable. Okay. So situations that fit binomial random variable. Okay. Oh, I'm sorry. So these are the conditions, and the random variable itself. Okay. The random variable is the number of successes that we have after n trials. So a binomial random variable could be, I flip a coin 6 times, how many times did it land on heads? Okay, so what possible answers, what are the values that this random variable can take on? Flip a coin 6 times, how many times did it land on heads? It could take on any number 0 through 6, right? So y can be any number from 0 to 6, or any whole number from 0 to 6, okay? And so I would need to set up a probability tree. Well, okay, so let's start off with an easier version of this question. And I say I flip a coin 3 times. All right, let's start off with 2 times, okay? And we say how many times did it go? How many heads? Okay, and the answer is the y can be 0, 1, or 2, right? And let's make a probability tree. Okay, so the first coin flip can go heads or tails, and it goes with probability 0.5, probability 0.5. And the second coin flip can go heads or tails, or heads or tails. Okay. And all of these probabilities are going to be 0.5, 0.5, 0.5, and 0.5. So far, so good? Okay. So heads ends up with probability 0.25. This is 0.25. This is 0.25. And this is 0.25. So if I flip a coin 2 times, how many times did I get? What is the probability that I get 0 heads? Okay. For that to happen, I would have to get tails, tails, and that would be 0.25. So I must get tails, tails, and the probability of that happening is 0.25. And over here, what's the probability that I get 1 head? Okay, I either can go tails, heads, or heads, tails. And so that would be the probability of this happening is 0.25, and the probability of this thing happening is 0.25. These are mutually exclusive events. Okay, if the coins landed heads, tails, they could not at the same time landed tails, heads. Okay, so those are mutually exclusive. So the OR probability is I just add those two together. And so I get 0.25 plus 0.25, and I get 0.5. And then the last one would be heads, heads. And I get 0.25. Is that okay?
Is that in any way reminiscent of quartiles?
No. This is just a random variable example. Okay, it's just a coincidence that we're getting 25% for all of these things. Okay. Here, let me modify this a tiny bit. Okay. And so let's say I have this weird coin that happens to land on heads with 70% probability. Okay. I don't think such a coin exists in the world, but let's say we have some magical coin lands heads 0.7, I'm sorry, lands heads with probability okay. Alright, so we can visualize this, right? Or conceptualize. Alright, so what if we do the same thing? I flip a coin 2 times. What is the how many heads do I get? Does it land heads? Okay, so I don't know how much time we have, but see if you can figure out the answers for 0, 1, and 2. Okay, and you can start off by drawing a probability tree.
want how many times it lands heads both times? Or just one time?
So you're flipping the coin twice, and so if we're asking how many times does the coin land heads, it either, at the end of 2 coin flips, it either landed heads 0 times, it landed heads 1 time, or it landed heads 2 times. Right? That's it. Or
So, I guess what I'm asking is, are we looking at, like, probability that it landed heads both times?
yeah, so if it
Or-
landed heads both times,
Mm-hmm.
then that means at the end of 2 coin flips, the number of times it landed heads
Mhm.
is 2 times.
Yes.
Yes. So, I think I'm answering your question, or not. I don't.
Sorry.
Okay, so I'm not sure if you guys are still working. Okay, so we're saying we're flipping a coin 2 times, and what I'm measuring at the end, I'm not measuring the individual coin flips. I mean, whether it went heads, tails, or tails, heads, or whatever. I'm just saying at the end of 2 coin flips, how many heads did I see? Okay, and so when I flipped a coin 2 times, there are 4 different things that could have happened. It could have gone heads, 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 tails, tails, heads, or tails, tails. Okay, but I'm not so concerned about the individual sequence, but just how many times did it land heads at the end of the day. So for me to say 0, then that means what happened in my sequence is that the first coin flip was tails and the second one was tails. Okay, that's the only way I could get 0 heads. And so that would happen with probability 0.3 times 0.3, so I get a total probability of 0.09. For me to end up with 1 head after 2 flips, that could happen in one of 2 ways. It could go tails, heads, or heads, tails. Either of those outcomes would give me 1 head at the end of 2 coin flips. This happens with probability 0.21. This happens with probability 0.21 for a total probability of 0.42. I do the same thing for getting 2 heads, 0.7 times 0.7, and I get 0.49. Are there questions on this? Is this okay? Okay, so what if, instead of saying I'm flipping the coin 2 times, let's say I flip the coin 4 times. Okay? And I said, well, find the probability of getting, the different number of heads. Okay, so we're still using this strange coin that lands 70% of the time on heads. Okay, so we're going to flip the coin 4 times. Okay, and I want to know, so the number of times that it lands on heads can either be 0, 1, 2, 3, or 4. So after 4 coin flips, I could end up with 0 heads, 1 head, 2 head, 3 heads, or 4 heads. We're good there. Okay. And if I were to make a probability tree, it would be a bit disastrous. Well, not disastrous, but it would be, we would say it's very tedious, right? So we have the first coin flip, and then we have the second coin flip, and then we have the third coin flip, and then we have the fourth coin flip. And if we count these up, there's a total of 16 different individual sequences that I would have to figure out. And then I would have to combine them into one of these 5 total number of heads. Okay? And so we want to kind of avoid this, all right? And we could see that if I said, well, I'm going to flip the coin 30 times, it would just be atrocious, okay? It would not be physically possible to do by hand. So So I'm going to try to illustrate what would end up happening, okay? Okay, so let's take a look at, let's say I'm flipping the coin 4 times, okay? 4 times, and I want to know what's the probability that I get 1 head. Probability of 1 head, after 4 flips. Okay, and I'm going to, for this scenario, I'm going to list out all possibilities, okay? So for me to get exactly 1 head, there are 4 ways this could happen. I get heads on the first flip, and then I get tails, tails, tails. Or maybe the first one is tails, but then I get heads on the second flip, and the remaining one are tails, okay? Or I get tails on the first 2, but the third one is heads, and then I get tails, or I get that, okay? So are we in agreement that these are the only possible ways for me to flip a coin 4 times and end up with 1 head? Okay? All right, and again, the probability of getting heads is 0.7, and the probability of getting tails would then be what? 0.3, okay? So what is the probability of getting this exact sequence? It would have to be 0.7 times 0.3 times 0.3 times 0.3. Okay? So it would be 0.7 times 0.3 raised to the third. Okay. What about this one? It's the same, okay? Because even though my order is technically 0.3 times 0.7 times 0.3 times 0.3, multiplication, the order doesn't matter, so this would also be 0.7 times 0.3 to the 3, and it would be the same for these other 2. Okay? So all 4 outcomes, all 4 sequences have the same probability. Okay? So the total probability of this scenario happening would be 4 times 0.7, technically to the 1, times 0.3 to the 3. Okay, so the outcome here would be 4 times 0.7 to the 1 times 0.3 to the 3.
Does it matter if they're how you multiply it?
What do you mean?
Like if you would it be you multiply the 4 times the times 0.7 times 0.3 to the third, or would it be just you multiply them straight?
So you just have to obey the order of operations.
Right.
Okay, so that means you do the exponentiation first,
Right. I just was wondering
and then you
if
do
there's,
the
like,
multiplication.
parentheses involved at all in these.
No. So yeah, just multiplication. The order of multiplication doesn't matter. Okay, just do the exponentiation first, and then you do the multiplication. Okay, so that's what we have there. All right. Okay. What about the probability of getting 2 heads after 4 flips? What is the probability that I get 2 heads after 4 flips? Okay, so this is a little, just a tiny bit harder, okay? So I'm going to list off all the possible ways to get 2 heads after 4 flips. I believe that is it. Okay. So this is all the ways to get two heads after 4 flips. Okay. And again, each of these, what is the probability of this exact sequence? 0.7 squared times 0.3 squared. Is that okay? Okay, because we have to get two heads. The probability of head is 0.7. And then each time we get tails, the probability of that is 0.3. Okay, and so we would have to get this, and then all of these would all be 0.7 squared times 0.3 squared. Okay, so all 6 have this same probability. So the total probability of all of this is 6 times 0.7 squared times 0.3 squared. Okay. Okay. Are we okay with this so far? All right. So the formula that we're going to use for binomial probabilities, okay, so in our binomial setup, we're doing n trials, okay? The probability of a success for one trial is p, okay? And we're going to calculate the probability of getting j successes. Okay. So in this scenario, we have n equal to 4, p is equal to 0.7, and j is equal to 1. And over here, n is equal to 4, p is 0.7, and j is equal to 2. So the probability of getting j successes after n trials, where each probability of success is p, that is going to be, well, I'm going to put this thing right here, okay, and I'll explain it, is p to the j times 1 minus p to the n minus j. Okay. And this first thing that we write here, this is read as n choose j, and I'll explain that in a bit. Okay, but we can kind of see that already, right? So I have this number here, 4, and I have a 6 here, but then the next part is probability of getting heads, or a success, is 0.7, and that happens one time. Probability of tails is 0.3, and that would need to happen 3 times. Okay? If I'm flipping the coin 4 times and I'm looking for exactly one head, that means I get heads 1 time and I get tails 3 times. If I flip the coin 4 times and I'm looking for 2 heads, then I would get heads twice and tails twice, and the probability of heads is 0.7, so 0.7 twice times the probability of tails, 0.3 twice. And the only thing that's different is that this first number is 4 and over here it's 6. And basically this is the number of ways I can arrange heads and tails so that I have 4 flips and 2 heads. Okay? So I can arrange, there's 6 different sequences, and that's where this number comes from. And in the other example, we had 4 different sequences. Okay? So the number of sequences, possible sequences, is represented by n choose j. This would be the number of sequences. The way we calculate n choose j, all right, well, I'm going to put the formula, okay, but chances are you have a calculator button that will make this easier for you. Okay, and so if you have the button on your calculator, just use that. Oh, and there's actually a table in the back of the book that you can also use. Okay, so on your calculator, there might be a button that you see that says NCR. Okay. Somewhere on your calculator you might have a button. You might have to hit the shift or the second function button. But it might say NCR. If you have a TI calculator, you might have a math or probability button. Okay. And so if you might have to hit the probability button and then use your arrow keys and look for the NCR function under probability. Okay, math or probability. And so you could do for NCR2, and it will say 6. Okay. So what does NCR mean? Or choose. What does this mean? N choose J. Okay. Okay. So for choose 2, you can think of it as, let's say there's 4 of you. You're hanging out. You're hanging out at your house, and you get hungry, and you say, "Oh, we're gonna send somebody to Taco Bell, okay, to get food for us, right?" But maybe the car only fits 2 people. Okay, so how many ways can you select 2 people to go? That would be 4 choose 2. There's 6 different ways you can select 2 people to go. Okay. If there's 6 of you and 5 can fit in the car, you would use 6 choose 5. Okay. 6 choose 5. How many ways are there to do 6 choose 5? Okay. So that might be tough to think in your head. Okay. But if you think of it as choosing 5 people to go in the car is the same thing as choosing 1 person to stay at home. Right? Okay. So 6 choose 5 is equivalent to 6 choose 1. Okay. And so if there's 6 people, how many ways are there to just choose 1 person? 6. Okay. You're just choosing 1 person, and so there's 6 different ways to pick 1 person if there's 6 of you. So 6 choose 1, or n choose 1 is always going to be n. Okay. And n choose j is always going to be the same thing as n choose n minus j. Okay, so 6 choose 5 is the same thing as doing 6 choose 1. All right, and so to answer any of these other things, we would just use this equation. So to get 3 here, the probability of getting 3, this would be 4 choose 3, 0.7 to the 3, and 1 minus 0.7, which is 0.3, to the n minus j, or 1. Is that okay? And we can apply it to these other situations as well. 4 choose 4, 0.7 to the 4, 0.3 to the 0. And here we would have 4 choose 0, 0.7 to the 0, 0.3 to the 4. Just filling in the rest of our probability tree, or probability table. You guys all look like you're suffering. Okay, does this make sense? Yes.
So the J over here on this board is the R over here?
Yes, on the calculator they use n choose R, okay? But in our book, the book uses J.
So that function basically just is doing that
Yeah,
calculation?
yeah, so NCR would be the equivalent of having n choose R.
Oh.
Okay, this is choose. It's written, it's n choose R. It's how many ways can you choose R things out of n things, out of the pool of n. Okay. All right. If I asked you to find the mean of this random variable, you could do it. You'd have to do 0 times the probability of this plus this times the probability. And you can do it that way. Or there's a shortcut And so for a binomial random variable, and this is only for a binomial random variable, the mean, mu, is equal to n times p, and the standard deviation, sigma, is equal to the square root of n times p times 1 minus p. Standard deviation. And those are shortcuts to get the mean and standard deviation. Yes?
To get P originally, you always have to at least do 1 out to get the 0.7?
No, the P should be stated somewhere in the problem.
Oh,
Okay, the P should be stated somewhere in the problem. And I know I spent a lot of time going over the calculations of this, but very important is knowing when to use the binomial random variable, okay, when this situation applies. And the key here is you are doing the same thing several times. You're doing it n times. And every time you do it, you have either a success or a failure. Either something happens or it doesn't. And we're looking for how many, what's the probability of getting j successes. So that's the, pay attention to when we use the binomial random variable. Okay, we'll see you guys next week. The details regarding the quiz are on the homework page. So we'll see you next week at 7 to start the quiz.